To complete the introduction of hypothesis testing and the 10 steps to answering a question with data, we'll round out with steps 7 through 10. Our essential questions are: what is phase 3 and what are steps 7 through 9? What is phase 4 and step 10? And what is the difference between steps 8 and 9? We've already in detail looked at phase 1, where we are stating the question, evaluating, describing the data, reviewing the assumptions with the data, and stating the question in the form of a hypothesis. We've looked at phase 2 on deciding how to answer the question, decide on our summary statistic. For us, it will be proportions with categorical variables. How will random variation affect that statistic? Remember, if what we see is due to chance, we expect to observe a proportion similar to the proportion we expected to see. And then we state a decision rule using the statistic. We'll now move into phase 3 about answering the question with 3 steps, and phase 4 about communicating the answer to that question. To review phases 1 and 2, remember to look at your data, errors, outliers, problems, and what questions can you answer with the data. If you are designing your study or your experiment, then you actually have a lot of choice as to what questions you can ask. If you're using data that has already been collected, you may be limited. For example, if you are looking at teacher absenteeism and how it affects state scores or test scores, if you're only provided with the fact that that teacher was absent or not at all, then you cannot answer the question if the days of absenteeism are related to the test score. So keep in mind about what questions can be answered. Look at the assumptions. So is your sample representative of the population at large? And are the units of observation independent of one another? Then define your statistical question in terms of H0 and HA. Step 4, pick your statistic. For us, it's a proportion with categorical outcomes. Again, understand random variation and the noise on what you expect to see. It may be a little less than or a little more than your null proportion, but if it's just random, it should be close to it. And then stating your decision rule in advance of answering the question means that you didn't go what's called fishing for a significant result. We will pick H0 if the p-value is large or larger than alpha. We will pick HA if the p-value is small or less than or equal to alpha. And remember, alpha is our decision rule, and it is what proportion of the time we are willing to incorrectly choose the alternative when the null is true. It's usually 5%, and it's chosen by the researcher in advance of looking at the data. Once we've done steps 1 through 6, we can start phase 3, which is actually answering the question. As you can tell, we've done more than half of the steps before we've even looked at our data. So we're going to return to what we did observe and recall our question. Does ECMO improve survival? Our hypotheses that we have stated with our decision rule from step 6, our null is the population survival proportion is 0.44 or less if the observed proportion is less than or equal to 0.4543. And our alternative is that the population survival proportion is larger than 0.44 if the observed proportion is greater than 0.543. So if we observed 49 or more survivors in our data, that's evidence for the alternative. If we observed 48 survivors or less in our data, that is evidence for the null. And this, of course, is based on the simulation that we looked at in the prior lecture. Step 7 is relatively quick. We calculate the statistic. In our case, we saw 57 out of 90 survivors. So P is 57 divided by 90, and that gives us a 0.633. Step 7 is complete. That takes us to step 8, where we make a decision, and this is making a statistical decision. Based on our simulated results, our observed proportion falls under the decision rule for rejecting the null hypothesis in favor of the alternative hypothesis. We are now abandoning our belief that the proportion is 0.44 and choosing to believe the alternative hypothesis. that the survival proportion when using ECMO is greater than 0.44 of our understanding of ARDS survival in general. Normally, we have an associated p-value, so we look at our distribution and determine what percentage of responses are as extreme as we observed, so 0.633 or greater. Therefore, our p-value here for our experiment is less than 1 in 1,000. So our p-value would be denoted as p-value less than 0.001. It's less than that because remember, we didn't actually observe anything larger than 1 in 1,000. We didn't observe a larger survival rate than 0.611. So the lowest we can go is 1 in 1,000. The chance of observing the data we observed, given our simulation results, is less than 1 in 1,000. That's pretty extreme. Our p-value, again, is the probability that randomness alone or chance alone leads us to a test statistic greater than or equal to what we observed. So if H0 is true, the p-value is the probability of the test statistic as extreme or more extreme than the one we observed. We compare the p-value to alpha. But remember, we have assumed that the null is true. We don't actually know which one is true. We're assuming the null hypothesis is true. Our p-value, no matter how small, does not prove to us what the truth is. P-values and significance levels are not going to tell you what is true in the grand scheme of the population. Statistics do not tell you the truth. They only help you make a decision between what you assume to be true and what your research question is. The p-value assumes the null hypothesis is true. And under that assumption, the p-value measures how likely the various outcomes are to occur. In our case, we saw a very small p-value. That tells us that the outcome we observed, that 63.3% survival with ECMO, is a very rare occurrence if the true survival rate is 44%. That leads us to the statistical decision. If the observed outcome is likely to happen, then you will usually choose to believe the null hypothesis. Of course, you could be wrong. Remember, you could be wrong. If the observed outcome is unlikely to happen, then you will choose to believe the alternative. Again, we could be wrong. This is where that concept of error, type 1 error, comes in. Our alpha level is how likely we are to choose the alternative when the null is really true. So we've chosen the alternative even though the null is really true. That's our alpha level. So now that we've picked HO or HA, how do we actually state what we believe? In our case, we've concluded with a very small p-value that our 63.3%, proportion 0.63, is very extreme and very unlikely to be 0.44. So we are going to choose the alternative hypothesis here. That's our statistical decision. We have rejected the null in favor of the alternative p less than 0.001. That is our statistical decision. That actually means nothing without context. That is step 9 and stating the conclusion. Our p-value is not the answer. There are any number of statistical experiments that could give us a p-value of less than 0.001. Simply stating we've rejected the null in favor of the alternative doesn't actually give an answer to your question. It needs to go back into terms that the question was stated, make it clear what you now believe. Remember, our question was, does ECMO improve the chances of survival? Our context is that we've rejected the null hypothesis of survival being 0.44 in favor of the rate being greater than 0.44. ECMO has an observed rate of 63.3% that is statistically significantly higher than 44% survival in ARDS patients. Note, We did not say ECMO survival rate has been proven to be 63.3%. All we are showing here is that our observed rate of 63% is higher than the assumed historical rate of 44%. They are, in fact, different statistically. We no longer believe it's 44%. We are now concluding that it is somewhere higher than 44%, and we observed it to be 63%. That takes us to the final phase and final step. All of the prior 3 phases each had 3 steps. Phase 4 has a single step. Communicate the answer to the question. This is the most important phase of this process because we need to communicate what we understand. We are the ones that collected the data. We are the ones that designed the experiment. We are the ones that have gone through steps 1 through 9. But we need to inform the rest of the scientific community, the media, other researchers, the lay public, what our results mean. So we formalized the precise question. We described how we were going to answer it. We used our data to actually answer the question, and now we need to talk about what that means. Step 10 is documenting your understanding with text, tables, or figures. This is a very simple or straightforward result here. So a paragraph would suffice. ECMO is administered to 90 participants with ARDS. Survival probability of ARDS victims without this intervention is 44%. In this study, the observed survival probability was 63.3%, which was a significant increase. And there's where your p-value is. All of what we did gets in the parentheses. Step 1 gave us 90 participants. Step 1 gave us 57 out of 90. Step 3 gave us our 44%. And the rest of the steps led us to our p-value decision. The final sentence would be ECMO improves the survival rate to 6 months compared to private estimates of ARDS survival. It is important to note that we didn't give a precise p-value here because of our simulation. We only know it will be lower than 0.001. Our simulation didn't exceed experiments with 57 survivors, but we did if we did it again. We could see that. Therefore, we're going to say it's less than 0.001. For this simple case study, there's no need for a table or a figure to explain the result, though you could include a table similar to the table they have in the published paper about who is in the study. What is the age? What is the gender? How long have they been sick? That type of information. It is very important that you state the final conclusion in addition to what the decision was statistically. Again, the p-value is not the answer. The p-value helps you answer the statistical question, but you need to actually put some context to your statistical decision. In this section, we used a case study and a simulation to go through the 10 steps to answer questions with data. Those steps are called hypothesis testing. This will be the basis of what we do for the remainder of this course and for what you do as a researcher. The steps ensure you don't overlook any of the important aspects of using data to answer a statistical question. If you skip one of the steps, I guarantee you, when you get down to answering the statistical question, something won't make sense, and you will have to go back and reevaluate your data. You may have to go back and reevaluate your assumptions. You may have formed your decision rule incorrectly. Do not skip the steps. However trivial they may seem, they are there to help you get to step 10 in a correct and defensible manner. The highlights of what we've talked about in this section. A statistic is any quantity that can be calculated from the observed data. For us in categorical data, it's a proportion. It's the number of events divided by the number total observations that you had. We will compare 2 sides of a research question. The null is the simplest explanation or our status quo of no difference or nothing new. It's what we currently believe. The alternative hypothesis is what we want to show. There is a difference. There is something new that is usually termed the research hypothesis. We will always assume the null is true. We will be looking for sufficient evidence from our data to change our minds and conclude the alternative. The p-value is what we use to make this decision between the null and alternative. We will compare our p-value to alpha. Alpha, again, is the probability that we choose the alternative when the null is true. So we are making an incorrect decision alpha percent of the time. It's usually 5% or 0.05. We'll fail to reject the null with a large p-value. We will reject the null and conclude the alternative with a small p-value. Remember, the p-value does not answer the question. You need to put the answer back in the context. And the p-value does not prove either one of the hypotheses. The p-value only gives us evidence to help us make a decision about which of the hypotheses we believe. Here we answered our question using simulated results specific to the ECMO study. Often it's not possible or practical to simulate every possible outcome. This was only 1,000 possibilities. And remember, we didn't even observe something as large as what we saw. We would need to do this 100,000 or 1,000,000 times to really have an accurate picture of what the likely ECMO results would be. So in the next section, we'll actually standardize the process and rely on these underlying named distributions. Most frequently, we will use the normal or the standard normal distribution, that bell-shaped curve that we almost saw here in our simulation, to use a formal set of steps in general so that we don't have to simulate everything every time. But we will continue to use the 10 steps, so review and make sure you know the order of the steps, how to look at your data, how to state your question, how to decide between your hypotheses, how to actually answer the question, and how to communicate the results of your analysis.